show. Hopefully you can see this. And we're going to talk long enough that it shows up on stupid YouTube, which takes several minutes to do. What are we going to talk about today, Ben? Put you on the spot.
Yeah, I'm on the spot. I haven't looked at our show notes yet, to be honest, because we're still, 15 minutes away.
We're still 15 minutes away.
We always have something to talk about. We're probably going to talk about some other books that we've been looking at, new technologies. I know I'm busy modeling a complex. You can see on my other screen here a data sheet for a Cliff audio jack. And
we are getting feedback that it's working.
Oh, cool. Yeah, it looks like it. Yes.
All right.
That. I'm just not. Oh, there it is.
Hey, Wes.
And I can see
it
Dave.
On
YouTube as well.
Yep.
Hey,
all
Dave.
Right.
Hey, Bill. So I'm going to get the link for our stream and post it on my LinkedIn channel as well, so people have a chance to tune in from there.
All right. And Chris just dated himself by talking about Memorex. Remember metal tapes? I still have my metal tape recorder that could do metal oxide.
Yeah, those were the best, actually.
Yeah, I have an old TAC.
I exclusively purchased those for my Walkman. And I never had a genuine Sony Walkman because they were really expensive in Australia. I had knockoffs of Sony's, and but we just called them all Walkman because Sony was the first one to come out with it, right?
Right. You know, we could probably just keep streaming here, or we could
why don't we do that?
Yeah, let's do that, because it might not work a second time. The chaos theory, actually quantum theory, right?
People talk to me about some of that stuff, and I need to read more, so I'll admit ignorance there. But I do have my own hypothesis about, and this is kind of off topic and a little bit political or religious, whatever you want to call it. But I have my own theory that, every particle in the universe that we know, and there's others that we're still discovering, right? So that's where my theory comes undone. But we do know this, that everything's held together by electromagnetic fields, pretty much. Or there's forces in the universe. There's the strong forces, so electromagnetics, and there's weak forces like gravity.
Right.
Weak forces and strong forces. But we understand these well enough now that if you could have a theoretically isolated situation with charged particles and their masses, and all of that can be known, even if you just had two particles that have an existing velocity and direction, and we know exactly can predict what those two particles will do next. In the next moment, infinitesimally small moment in time, we know mathematically where they're going to go. Because we know about the charges, we know about their behavior, their mass, we know about gravity. And so it's theoretically possible, based on that knowledge, that if you could know exactly where every particle in the universe is right now, this moment, and all of those particles have a known finite mass, a known finite charge, then one could predict in the next infinitesimally small moment
the universe.
One could exactly predict what's happening in the future.
Except for quantum effect.
But there is no, well, that's where I'm getting at, that I haven't read up enough on that. The people talk about uncertainty principles and all of that, saying, but I actually have my own hypothesis that those are just human constructs that make us feel better about the fact that our brains aren't big enough to know where everything is right now and where they're going to be.
Did you ever read Hitchhiker's Guide to the Galaxy?
I did.
Yeah, they talked about the great computers, and a mere abacus, it predicted every atom since the Big Bang. He goes, a mere abacus compared to me.
Yes, it's like that. So
Hey, so I have to say, I'm going to expand this a second. I just got a refresher in all subatomic particles, including dark energy, dark matter, WIMPs, where they think it's a weakly interactive massive particle, by
I
Dr.
love that.
Sean Carroll.
A WIMP.
Yeah.
Brilliant.
So I recommend this course. It's for free on Amazon Prime. If you go to
No
the great...
way.
Yes.
Well, I have Prime, so I'm definitely going to look that up.
Yeah. They have the great
Higgs
courses
boson.
as a subcategory, and it's only a sampling, but it worked because I went and bought some of these then, about stuff I didn't know, basically. So, gravity isn't a force.
Oh.
So in the Higgs boson series, they do predict the graviton. And they talk a lot about everything's a field until you go to measure it. At the time you measure it, it becomes a particle. And in theory, that explains interference lines when from slits. How can photons interact with each other if they're not waves, and yet they act like photons at the end of the day?
Yeah, it's amazing, isn't it?
It really is. So what I learned about the Higgs boson, though, is it's got the most potential energy in empty space. Unlike every other force, if the space is empty, the Higgs boson has a value of like 2 or something. And the more matter is in the Higgs boson field, the less potential energy it has. And so it's interesting. And to me, if I were to write a science fiction story, I'd write that magic is just the interpretation of the Higgs field, I should say. The boson's a particle realization of the field. So magic in the world.
Yeah, the knowing enough to manipulate things that were previously unseen, or maybe they're still unseen because they're too small for us to see them.
Yeah.
But that's
or
what
too high energy.
That's exactly what electronics is all about and why we love it, right? You get to do what in prior centuries would have been called sorcery, and you'd have been burned at the stake for doing it.
Right. Or classified, a heretic,
Yeah.
So there's my plug for the Higgs stuff.
You've got your soda already, but I need to go get a glass of water or something.
All right.
And we've already got a small crowd gathering, but I don't know if you mind, Bill, entertaining the crowd while I go grab some water. I'd love that.
All right. I can do a song and dance.
Cool.
Oh,
Be
what
right
kind
back.
of PC boards do I have here? Oh, that's the Radar PC board itself. I didn't ever show that. It's got the actual voltage-controlled oscillator. It's got the RF amplifier for transmitting, and it's got the RF amplifier for receiving, and then it's got the mixer to super heterodyne those two 2.4 gig signals and turn it into a true audio signal. And actually, you can plug it into the audio input of a laptop and do your math manipulation on a laptop, whether in real time or behind the time. It ends up to be behind the time, but I want to stick an FPGA in there that does the fast Fourier transforms and does the decimation or whatever's needed. We can drop an FPGA right in series, and it can either pass the audio straight through, or it can do the math that we need to do for showing Doppler radar. This is a continuous wave radar, which means that we tag it so we know when it left and when it returned, so we know distance. But then we also look at the frequency variation, and that gives us the speed of the object. All from just a little tiny thing. These things could be built into a lot of things. Typically cars, though, don't work down at 2.4, there's radar in cars. They're up around 80 gig. What have you heard for some of the car radars? 60 to 80 gig, I've heard.
Yeah, it's. I thought it was millimeter wave, so that is in that range.
Yeah. Yep. Explain what millimeter wave means.
Well, the wavelength of the signal you're dealing with is down in the millimeters sort of range.
Right.
Technically, every wavelength could be given in millimeters.
Right. Just it'd be really, really big in some cases.
It's like
meters
what we're
long.
dealing with. So, what frequencies would that be? Let's do
Planck's constant. Every time I look at my microwave oven and I see the little holes in the shield, see, my mind goes Planck's constant. If you were to derive that, you'd know the frequency of the oven by the virtue that the holes block the frequency.
Well, the holes have to be small enough that they are basically, it appears like a solid sheet.
Right. It's not an aperture for once. Yes.
Yeah. Yeah. So.
Oh, we could talk about apertures. Apertures were the big thing back in the 70s. You went around with copper tape and beryllium springs, the RF gasketry, and went around looking for all your apertures. And an aperture could even be where two sheets of metal, like if you have a folded metal case, where those two sheets join, if you don't have a good continuous ground on them, like there's an oxide between them, it looks to the eye like it's just a slice. There's RF energy pouring out of it. SAR, anyone? I forget what SAR. Synthetic aperture radar, right, Chris? Yeah, so you can do SAR using this technique, but you need two receiver transmitters, and the distance between them starts to help triangulate everything. By the way, I'm just copying. I did the design of the radar, but I'm copying the work done for what's called MIT's FMCW, frequency modulated continuous wave radar. So, how's that for filling time?
Whoa, there you go.
So you're back. You got your water.
Yep.
Hey,
actually, I ended up getting water, but it's dark brown and has other stuff in it, including caffeine.
So that rolls out beer, right?
No.
Even Australian beers.
Well, they're not the greatest.
Hey, well, have you ever heard the Monty Python skit on Australian wine?
No, I haven't.
It's wonderful. It's like a bully of a wine that'll climb out of the bottle and smack the shoot out of you. You know, I mean, they just have these adjectives to describe Australian wines that are hysterical.
I'll have to look that one up.
All right, John Smith's back. Trump lost, Biden won. Get over it. Yeah. Sorry, guys. We don't know who he is.
This isn't a political show.
Yeah. Yeah, if Mike's on, he's empowered to delete that while we're talking. So, I have some books here today, too. We'll wait a little bit.
What you've been reading.
Well, what I read years ago.
I'm picturing you sitting up in your bed at night in winter with the little light on and your book and you're reading light.
Even when we took vacations, I would pack every nook in the car with data books because I used to sit and read data books. And it got to where I could lay on my right side one night and read the left pages, and the next night I'd lay on my right side and read the other pages. And my memory was good enough I could put it together, but that was a lot of alcohol ago.
I don't know why people do things like that, honestly, Bill, but maybe I'm just too pragmatic.
What, alcohol?
No, that I understand.
Well, I got tired of leading up for every other page.
I just have to respond to Chris's comment about American beer. I live in San Diego, which is the craft beer capital of the world. So, American beer, what I thought of before I left Australia and started living in San Diego, California, I thought the same thing. I thought it was all Miller and Bud and Coors, and I don't touch any of those. They're boring. They might as well be mineral water. So yeah.
Back when I worked at Commodore,
if you still think that about American beer, it means you haven't had a good IPA or something full of flavor like what they do.
Yeah.
And those are a take it or leave it thing, but that's what I like. But
yeah, my memory of IPAs is I couldn't stand them. That citrusy, hoppy taste.
Oh, I love it. Lots of flavor.
Yeah. I was a Michelob drinker back in the day, back when the bottles were tear-shaped.
See, that's not good beer. I'm sorry.
It was my favorite beer. Them's
the thing
fighting
you buy
words.
if you want to. No, that's what you buy if you want to make a makeshift battery.
Yeah. Well, I liked things like Yangling too and whatnot, but you know, when you're an alcoholic, pretty much anything will go. So
You saying you were an alcoholic?
I still am.
Oh, I didn't know that.
Yeah. Yep.
So you
So,
haven't touched a drop in how long?
I went 25 years and then I picked up for 3 years, and that was several years ago. I just had to go out and try the IPAs and everything before I got too old to enjoy them. So I drank for a couple of years and then stopped.
Well, good for you to be able to, to have the discipline to do that. I've heard that there's a lot of other people who are, reformed drinkers who still do have one or two here or there. But as a teenager, when I heard about AA and sort of learnt more about this sort of ways of the world, I had this belief that if one really had a problem like that, then it was a lifelong thing, and you
Yep.
basically had to realize you just can't do that.
Once you've triggered they say there's some disposition genetically, but then you still have to do the act of drinking to be, or other drugs, if you're an addict in those ways, you still have to activate the mechanism through abuse. And then once you have, that's it for life, is the way I look at it. Other people can look at it different. That's how I choose to look at it. So, yeah, it was an all or nothing thing for me, which is how I have lived my life.
Wow.
So now we did have a San Francisco beer in the
that we're going live right now. Sorry, hold that thought.
Yep. Somebody just posted I don't have a problem with alcohol. Well, I used to say I didn't have a drinking problem. I drank just fine. So it was.
That reminds me of Airplane, or in Australia, the movie was called Flying High, which is a much better name for that movie.
So,
I guess name was ruled out for the American market because people were much more conservative in the mid-70s when it came out, or whenever it was. But
right.
In Flying High or Airplane, there's this scene where he's telling his story. That's when my drinking problem began.
Right.
It flashes to a scene where
he misses his head. Yeah. So, yeah, back at Commodore, one day I counted up how many of us were alcoholics, and it was about 50%, which begs the question, did alcoholics do really well at Commodore, or did Commodore actually turn you into an alcoholic? And the jury's still out on that one.
I would say it probably depends on the individual. It reminds me, I went to, and all due respect to Dassault and Solidworks, they make great products and everything. But so this was just purely a joke from an insider. I went to a Solidworks world many years ago with Altium when we were launching a product called PCB Works, which is now Solidworks PCB. And the field applications engineer I was co-demoing with, who was the Solidworks expert, he said, "Have you ever been to Solidworks World before?" I said, I manned a booth at one years ago in San Diego, and this was in Phoenix at the time. He said, "Well, just so you know, because we're in the main shop floor, just so you know, Solidworks is a drinking company with a CAD problem." So that was a joke. It was nothing like that, of course. They just had, it was like PCB West, at 5 p.m. some beer carts rolled out. So it really wasn't like that at all. But anyway,
right.
I just thought that was very amusing.
Didn't you do a presentation not too long ago? It was virtual, but what was it for, PCB Con or something like that?
Yeah, PCB West.
That's it.
I did a full one-day presentation, and it's just not the same virtually, no. I've got to say. But it was on RF and microwave PCB design. And I do the same one for IPC Apex Expo and for DesignCon. And they're always well attended because there's a lot of people who do board layout and know signal integrity. They know, digital design. They know how to get, tens of gigabits per second across a board and successfully out the connector or into the backplane. But they also know one of these days they're probably going to have to do some basic front end analog section for RF,
right.
and really there's no straight up how to or textbooks. Like, that's the weird thing about the board level electronics design. People get their engineering training. They go to school and get either an associate's degree or a degree in electrical engineering, or they learn on the job like you did, and you learn a lot about electronics, and you learn, and really you're thinking about the circuits and the circuits function, like the op amps and transistors and microcontrollers and all of that. You understand, and you can draw a schematic and know what's going on, and you can plan what you're doing. But when it comes to the board layout, no one ever taught that, because the prevailing attitude of all the educational institutions all throughout, since printed circuit boards were begun, is, oh yeah, so you design the electronics and then you hand your schematic to a PCB designer and they'll lay out. They're a tool expert and they'll use their tape and Mylar or their CAD software and lay out the board. And that's how it was for decades, because they could just join the dots. Basically, their job was to design a connection pattern and solve the puzzle.
That's right. That's right.
But now, and it's been this way for the last 15 years in my thinking, it was really as much as 15 years ago, things started getting fast enough that you actually have to understand some...
Right. It's changed.
Yeah, you have to understand some electromagnetics at least, or basic signal integrity. And so, but now we're at that next phase of that, where more and more people are doing IoT stuff and you have to make a tiny sensor board that's going to pass EMI. It has to
pass the FCC part that relates to transmitters too. It's not just about EMC.
Right.
It's about the fact you have a licensed transmitter.
Yeah, so
not licensed, but certified.
They don't have to be in the ISM bands at below a
certain power.
Yeah,
but they have to be tested to be below that certain power. That's why there's an FCC ID on there, and they have to be tested to make sure they're in the ISM band. Which for everybody, that's like around the 2.4. That's your microwave oven, Bluetooth, wireless LAN, some of wireless LAN. Hey, so I wanted to show this, not that I work for the great courses or not, but here's another one that was, whoops, come here, you. Well, it's on the great courses called Modern Electronics, and the guy steps through everything, including op amps, flip-flops. It's a good course for somebody just want to see if they're into electronics. And this one was also free on Amazon Prime when I last watched it. So I actually did, skim through most of the episodes just to get a good refresher going.
That's cool.
Yeah.
Of course, there's always YouTube. There's Masterclass. I've been disappointed. I'm a Masterclass subscriber. And I got onto Masterclass because they had... Excuse me, I'm still reeling from that liquid.
Yeah, pure water can do that to people. That's why I used to drink beer.
Oh, well, I'm talking coffee, but yeah, coffee in the windpipe, not so good. Anyway, Masterclass have had all these celebrities showing, how to direct films, how to do writing, and they've got some, I got onto it because they had a music production one with Deadmau5, and I just thought that would be really fascinating. And then some other songwriting ones, but they've had the celebrity astronaut from NASA, how to be an astronaut, a masterclass. Like, okay, really, that's just an extended documentary. Let's be honest.
Yeah.
And for all the acting, for all the acting and film related ones, it's just they're giving some practical tips, but it's no substitute for a proper film school where you get right down into the details and the depth that you need for understanding even equipment, all the different jobs in filmmaking, what grips do, what gaffers do, and all that stuff. But then I'm thinking, surely by now, after 3 or 4 years of this, there's got to be a masterclass on electronics, and they still don't have one.
Right.
Because electronics is becoming it's become a popular hobby again.
With the maker movement, yeah.
And there's a lot of people. Just the fact that YouTube channels are thriving, like Robert Feranix,
right,
or Dave Jones, they're really thriving. They couldn't exist if it wasn't a popular enough sort of topic.
Right. And Dave Jones's reaches up and down. You can get something out of it if you're really good at electronics, or if you're just starting out or looking for an answer. A lot of people go to his EV blog, and he's got way more energy than I do. I couldn't produce the number of videos in this time scale he does either. So
the difference there is he does it full time. Since he
yes.
He was let go by Altium, unfortunately, because he's a great designer. Back in, I think it was early 2011, when they decided to relocate from Sydney to Shanghai. And there were people who were asked to move to Shanghai, and if they didn't want to move to Shanghai with their families, they were
right.
Basically, most of them were like, well, this is where the company's going, so you'll have to find another job if you're staying in Sydney. And that was something that Dave Jones, had to face. But the blog was already popular enough then, and I remember the day
dihydrogen monoxide's water.
Yeah.
Go ahead. Yeah. I'm talking to the chatters.
I remember the day he sent me an email saying, looks like I'm out. And I said, well, you must double down on EEV blog. Don't go find some other job that's like, clearly this is big enough and popular enough. He had told me how much money extra he'd made on it the year before, and just doing it on the side, it was enough that it's like, if you do this full time, you could quadruple that amount, and that will be more than what Altium's paying you. So just do it.
Yeah.
He's like, I'm just having to convince the wife that that's a good idea, but he did, and now look where he is. So
yeah,
and now I'm not the reason. He would have done that anyway. Everyone, it wasn't just me. Everyone was saying, Dave, you've got to do this. Like this is a thing. So I'm not taking credit for him doing that. He would have done it anyway, but.
Yeah, and I've been on that podcast that he does. I can't remember the name of the podcast, though. I had the ruler here.
It's with Chris Gamble, the Amp Hour.
Yes, yeah, with Gamble.
Yep.
Amp Hour. And they've had some amazing people on there. If anybody's watching this and you want to see, David or Ott himself was on the show. I keep waving the books around. He was still alive. I don't know if he still is, but people like him have been on the show. They find amazing people to talk to. So,
yeah.
Hey, Osh
You're looking
Park.
at a layer stack again.
Osh Park has a 6-layer stack coming out.
Is this the spec that they gave you?
Yes. Well, I built this up from the spec they gave me. And you had made a good point of saying that a 6-layer is way better than a 4-layer. And I thought that this actually kind of shows that if we know what we're looking for. Do you want to tell us about why?
Let's go through this layer stack you've built here.
Yeah. So go ahead.
So
you're better at this than me.
Yeah. When the board fabs are building up the PCB, they generally start, almost always they use what's called a build-up. And there's 2 ways of doing a 6-layer board, but you've got the build-up.
Right.
The darker dielectrics are cores, and the lighter dielectrics are prepregs.
Right.
So generally speaking, they start with 2 cores, which are very thin, that are pre-clad with copper. They etch and drill those, or drill and then plate and then etch them to get your inner 4 layers of copper pattern. Then they build up prepregs between the top core and the bottom core, and maybe some combination of core and prepreg in the middle, which is what you're showing. And they will laminate that to get the first 4 layers. And now cores typically, like you've got 4 mil cores there. That's about as thin as you're going to get in a core. If you want thinner, you could probably go down to 2 mil thick, and that's just going to be 1 layer of prepreg. And they build up the thickness you want by adding more and more prepregs to the lamination stack, and then going in the hydraulic press with heat and pressure to get them to squeeze out to the tolerance you're asking for. And it's the PCB fabricator's secret sauce how they do that, and how they can accurately predict exactly what thickness it's going to be.
Right,
and
right.
How many combinations of core and prepreg with different types of glass fibers that they can use to get it. So then they put prepregs on the outside and copper foil on the very outside, and they laminate that. Then they do a final drill, plate, and etch to plate right through the board and the outer layers. And then, of course, there's also the solder mask and the preservative, which is your ENIG or hot air leveling. But why is this a better layer stack for signal integrity? It's because you can, if you want, make strip lines. So that second layer in, you could have shielding copper on the topmost layer and shielding on the next layer down. So if you want to do controlled impedance strip lines, you can do that. Or if you need power and ground, but you need a reference plane, normally the reference plane, your ground plane, is going to be the second layer.
Right.
That second layer should be a plane layer normally, because then you get microstrip lines above and beneath it, and both can be controlled impedance, and you can switch layers routing, and it's all with one shared reference plane, so it's far better for signal integrity, and you can switch layers without popping in extra vias for ground for your signal integrity vias, because you go from the top layer to layer 3, but layer 2 for both layer 1 and 3 is your reference ground. So the ground doesn't change layer. The ground return path in your signal doesn't change layer. Only the signal itself changes layer. So, but it also gives you, maybe on the other side of the board, you might run your analog and your power and grounds as well. So you have these extra layers that you can use for more shielding from sensitive signals, but also running your power supplies.
Right, right.
Yeah,
now I turned it into a power plane for you. Yeah.
Yeah, this is
how
I would do it.
The reason it was a signal plane when I initially started was I asked Ashpark, and they prefer the power planes and reference planes to be in what's called positive artwork. And in Altium, that means I need to make it a signal layer, whereas if it was a plane, it'd be negative, meaning wherever there's a via or something like that, it's the trace, it's the absence of copper, whereas on signal planes, we draw copper.
That's kind of a legacy thing. And normally I would just make them all normal layers, and then I make the plane by putting a polygon there. And I would do the same in Eagle or Fusion 360 as well.
The one thing I'll say there is when you work with negative planes, you have the ability to screw up a PC board really, really well. I've seen
there's no
massive
good reason
shorts.
There's no real good reason to use negative plane layers anymore. You don't need it for planning signal integrity. The layer stack manager or design rules are based on where you are calculating from a certain layer. It's not looking at that and saying, well, that must be the negative plane. It's like, no, I'm telling the software this is the plane layer. And I can, if I want, then do some additional signal routing there if I just need to get one more thing done.
But we both know how dangerous that is.
Without splitting up the return path, of course.
That's right. So how can we have two return paths here if one of these is +5, let's say, or +3.3, this one, and the second layer is ground? How do I get control the impedance down here if the ground's all the way up here?
You have to couple them.
Yeah. So I guess where I'm headed is the voltage plane is also a reference plane. You can do impedance to it, yes?
You can, but you have to be very, very careful that it is properly coupled. And that's where decoupling caps and measuring your plane impedances or simulating your plane impedances might be something you want to look at doing, because you're now saying, well, my 5 volt or 3.3 volt plane is a return path for AC, but the AC has to be able to travel.
Has to complete a path.
It has to complete the whole loop.
Yeah.
And that means it's going to be going through your capacitors between VCC and ground. And if those capacitors, if there's
noise on there,
if they're not placed properly, or if they're not the right values, or if there aren't enough of them,
right?
At that point it gets very difficult. But in this is also why I prefer a 6-layer board than a 4. With a 6-layer board, you can have 2 ground planes because you have enough area in most designs with 4 signal layers and 2 ground reference planes. With those 4 layers, you have enough space usually to get your power and signals done.
Right.
And then, but with a 4-layer board, the inner 2 layers still need to be ground for signal integrity, which if your board's big enough and you've got the room to route your power and signals on top and bottom only, then fine.
Right. Yeah. Right. So now in Ott's book, he says rarely would you go to 8 layers unless you're adding shielding for EMI. But since he wrote that, the use of multiple voltages like 5 and 3.3 or 3.3 and 1.8 have occurred more often. And so I'd say that 8 layers has become useful. We take one of these cores and now we drop in signal plane signal again, signal plane signal, and we've got multiple voltages.
You're going to have 2 more layers. You'll have 2 build-ups.
Yeah.
Did you just stop streaming?
No. There we're back.
Okay. I don't know what happened.
Yeah, that was scary, wasn't it? It makes me think maybe they're using SolarWinds over at YouTube. That's a security joke.
So with an 8-layer board, you have 2 more very close inner layers. And that's where you start to be able to use things like, a ground and a power plane right in the middle of the board with a thin dielectric between them for lots of capacitance. But then you're still going through long via barrels to get your power into the devices. So,
there we go. There's an 8-layer.
Yeah.
So I'm doing all this in Altium. By the way, everybody, they do have a great layer stack visualizer. I can even and I can show the real heights involved. And let's see if there's something else we can do. Oh, 3D, that's what I was trying to do. So, but you were going to show something other than Altium today, right?
Originally.
Okay. Don't mean to put you on the spot there.
Well, yeah, but you do. I know you do.
I'm sorry, it's inherent in the equation. All right. Here's a 1973 data book. This is one of my originals, Linear Applications, Volume 1. And this is my personal book from 1973. How old were you in 1973?
-1. How does your wife let you keep all that stuff?
We have a big basement. We have a huge. I have over 400 data books. I used to have over 600, so I've gotten rid of 200 of them.
That's good. What's going to happen to the rest?
I should find somebody that would appreciate them. I don't know. Do you think if I signed them and put them up on eBay, I mean hardbound TTL book from the 70s or 80s, that'd be worth it?
The other option is, and I don't know if someone's probably already done this, but they could all get, like, you could send them, I don't know, to have all the spines cut off them and then have them scanned in.
Wouldn't that be piracy?
Your facial expression was like, I couldn't bear to do it.
Well, it sounds like a lot of work to have TI come after me for copying data books. Actually, look what this says up in the top corner.
My goodness, Radio Shack.
Yeah, I bought this at Radio Shack. Yeah, they used to have their Nationals data books for sale right in Radio Shack. So I got that before I were a true engineer. And the way I became an engineer, I started as an associate engineer, is I was out in production. They used a part wrong, and rather than complain, I wrote up a thing saying, no, you're using the wrong chip enable for battery backup. So they had to interview me, basically, when a job opened up. And I think he was just going through the motions. And as the interview progressed, finally, he draws an op-amp circuit, and he's, and we're talking about the gain. I knew how to set the gain, and he said, there's something wrong with this op-amp circuit. I said, well, your input bias currents aren't equal. You'll have a temperature component. And I saw his body language change. That's when I became an associate engineer, when I knew that you can't just ground an input and have a 10K other input. Those are unequal bias currents. Even though it works mathematically in real life, you want a 10K on both inputs. I'm paraphrasing, but
yep.
So that was the day I got.
I'm trying to bring up, because I left it open all week in preparation for this, the Oshpark page that we were discussing.
Right.
And now do you still have that link, Bill?
No, I never had the link. That was you. I had something directly from Drew.
Oh, sorry. Okay. Yeah, they haven't published their 6-layer stack yet.
They haven't. No.
Okay.
And so I did do a test board with them. I got your notes on what to do in a coupon too late to get it turned in.
Oh, so you gave them something, though, that you can measure.
Yeah, so I'm going to measure impedance on a couple different layers, which is no biggie, but I'm still going to do it anyways.
Well,
so here's a 2-layer board.
So you're doing 2 layers?
No, I just changed the preset to 2-layer to show if I get the real stack height. Here's the problem with a 2-layer board. How do you control the impedance when the distance between the top layer and the bottom layer are so great?
You have to use coplanar waveguides.
Yeah.
So you have to surround. And Rick Hartley actually presented on this at PCB West and showed an actual design he worked on for someone that did a phenomenal job of this. They really wanted to go low cost, mass-produced consumer product, 2 layers. Not a super complex board, but just a little bit of it, like the USB 2.0 part, required some impedance control. And he used coplanar waveguides to do it, shielding around the differential pair.
Right.
and
Right.
ground vias down to the opposite layer. And the size of the board was large enough that he had the room to do that. But it is possible. And the other tip he gave was running things in threes. So you have two high-speed signals. You can run a ground line between them, and
Right.
here and there at fractions of a wavelength. It can't be very. They have to be reasonably close together, but they can be kind of random. You have ground stitching vias along it, and that gives you have one trace, and its reference return path right next to it on the same layer. And so
Right.
that's another way of getting away with doing it when you're only on two layers.
Can you talk about how to make what a blind via? I'm showing one here. How to make one and why they're useful?
How fabs make blind vias?
Yeah, because obviously you don't just drill through the board.
Well,
after
some
the board's
do.
made.
So that's backdrilling, controlled depth backdrilling, but that's super expensive because every board has to stop and have this process done after it's all etched. So that's different, actually. Controlled depth backdrilling is getting rid of via barrels so you don't have stubs on high-speed signals.
Right.
So,
the part that would normally be here is drilled out.
Early technology for blind vias sort of 10 15 years ago, some fabs were doing controlled depth drilling and then replating. That's really not the best way to do it. These days you have different, again, it comes down to you're starting with cores, and those get laminated together with additional prepregs and copper foil. The cores, each core represents a drilling opportunity in the design. So the economical approach is if you have a core build-up stack up where you start with two cores with copper on each side, those can be drilled and plated, and then those are laminated together with prepreg, and that's a slightly more expensive than the 4-layer process where you start with a core in the middle, or even 6-layer or 8-layer. You start with a core in the middle, and it can have buried vias. So a buried via is symmetrical, it's right in the middle of the board. It's through the core, and then they laminate over that several different layers symmetrically on each side. Other than that, if you're doing blind vias, I'd say you're probably, you might as well just go straight to using HDI micro vias, which are laser drilled, that go maximum 2 layers deep. They only have to drill through one very thin layer of prepreg that's on the outer layer. There's the copper pad of that via on the inner layer is actually a capture pad that, because it's copper, it reflects the laser. So controlled sort of laser drilled microvias are actually very fast and economical to make. They're still horrendously expensive to prototype. But if you're doing, and they're very expensive for short runs, but for mass-produced consumer electronics, they're super cheap because they have big laser machines that just blast through them really quick. And so there is that knee, that curve where there's a break-even point. Is this worthwhile or not? Do I really need to do this? Otherwise, blind vias force you to use a multiple core-based stack up, which has other difficulties and costs associated with it. So if you want mechanically drilled blind vias on the outside layers that go down into the next layer, the fabricator will almost always start with a core on the outer layers and try to laminate in prepregs in the middle. And that's going to that drives up cost, because why do things get expensive? They get expensive because there's more scrap. Why is there more scrap? Because you tell them it has to be this impedance plus or minus 10%. And maybe a third of the boards on the outer edges of the panel don't come within that 10%, so they have to throw them out. And you don't see any of that. They just charge you money for it.
It's a lot of money sometimes, yeah.
Yeah, because you might say, I want you to build this. And they go, okay, we can build that. It'll cost you this much, and it's really expensive. You go, well, it'll cost what it'll cost, so we have to build this thing, so go ahead. And what you don't see is that they're running maybe 5-hole panels, 18 by 24-inch panels, through their system to get one board that meets your specification.
It's like making chips in the old days.
You may not know that.
Right.
I'm sure I'm exaggerating the problem, but that's what's happening. It's all about managing scrap. Because especially here in America, pretty much all the fabs have to be squeaky clean. And their only exhaust material for some of them is water.
Right.
So everything gets minced, everything that's wasted gets minced up, mashed up, and they recycle all the copper, all the gold, all the other metals out of it. The glass, it's very hard to do this, but they probably burn down the
make sand out of it
and glass and sort of extract glass back out of that somehow and wash it. There's a lot of science, a lot of material science to that, and some of these fabs are incredible what they do now. Of course, overseas they're not nearly that clean.
And in New Jersey, we're pretty much not allowed to have plating companies like chrome plating. And I think that extends to PCB fab. I've heard there's not really any PCB fab here in Jersey, just due to the regulations in this state. And it's heavy metal regulations mostly, is my understanding. So
it's tough.
So show us why we would want to backdrill. What's different between this long via that goes through all 8 layers here and a short via? Why is the short one, other than density, why do we like short vias? If I only wanted to go to plane 2, why should I backdrill?
That second layer, if you're transitioning a signal that's a high-speed signal to another layer.
Right, like it comes in here and goes out there, right?
It may be impedance controlled, or maybe it's not, but it's a high-speed signal. That huge long via barrel that goes all the way through the board is causing reflections because it's a stub on your net.
Right, here.
It's a big long stub that just ends at the other side of the board. And
so it becomes an antenna too.
It can be an antenna. It depends on the length and the thickness of your board, what it does. It can also act as a notch. At some frequencies, we know stubs act as notch filters. So it's bad for signal integrity, is the bottom line. Right. Now, there's another easier, cheaper way around that. It's to always go, don't ever just go to the second layer when you're routing high-speed nets. If you've got all through-hole vias, you go all the way to the bottom and route some there, and then all the way back up to the top if you need to. So go through the via. But then you have other concerns. You need to place extra vias for the ground return path to not be broken up.
That's right. So you have to border around it with ground returns.
You make these trade-offs. You either go all the way through the board with an extra ground via right next to it to maintain return path.
Yeah.
Or a coax of them. If it's a really high-speed net, you might need to do that. But then you're dealing with managing board space and routability. Or you try to keep everything on one layer as much as possible. Or you may be forced to use blind vias, and then you're going to drive up the cost of the board pretty significantly.
Hey, do you remember, well, you probably do, on Altium, I'm having trouble here. I show a blind via between layers 1 and 2, but I can't make this one into a different pair. How do I bring up a blind via for like 3 and 4 or something like that? So when I hit plus, it just keeps creating. It keeps creating them on the same layers.
To edit it.
Okay.
You have to use the property. You don't have your properties panel open.
It keeps closing it. You know about. There There you are. So I can go doink. Ah, very good.
Now, Bill, I have to do this because you're just all Altium right now, and I work for Autodesk.
Well, show us Autodesk.
I'm just gonna call out the elephant in the room here and say, can you got to let me share my screen for a second?
Absolutely. Whoops. Matter of fact, I'm set up. If you share your screen now, it should show up.
I thought I was sharing it on Skype.
There it is. See, I was hiding it.
Oh yeah,
so
I was looking at Oshpark. Let me change to Fusion 360 real quick.
Very cool. We've been waiting to see it.
I know. And I don't have a good design right open today.
Whoops.
A clone of a stomp box I started working on during the week. So this is more a hobby design. Right? It's a octave up fuzz. But so nothing fancy. It's not my intelligent display, which I will show in maybe a week or two after. I'm having a bit of a break, so I'll have some time to work on that and get that design finished. But I will point out that in design rules in Fusion 360, it's a lot simpler. Of course, this came from Eagle, but it does give you everything you need to do that. So there's different layer sets, and we can preview those and preview how they're built up with cores and prepregs.
Right.
And we can also add, 1 to 2. We can add micro vias, and it gives us a 2D preview of this as well. So really, any tool with oil in its lamp, any ECAD tool with oil in its lamp is going to give you the ability to quickly see and plan how this is going to look. And you'll notice that the default here, when I went to 6 layers, it gave me a 1.5 millimeter thick prepreg on the top. Naturally, I'm going to go through here and modify all these layer thicknesses to reflect what Oshpark or whatever the fab is that I'm going to be using. But the cool thing about that is a lot of these fabs, starting the trend with Euro circuits actually in Europe, but there's a lot of these fabs, you go to their websites and they have downloadable files. So Oshpark has this for Eagle, which works with Fusion 360 as well. They have templates for their layer stacks that they support, including all the drilling and stuff like that, and some of the design rules.
Yeah.
So if you know which fab you're targeting or which quick turn prototyping service, if it's one of them, they ought to have a downloadable rule file that you can just plug right in. Euro Circuits has full-on DRU files you can download that plug into Eagle and to Fusion 360 that set up every single thing that according to what their fabrication service can offer with annular rings and everything. It's all pre-done. So then you can go and modify at your own risk, but modify with your own knowledge about what it is you're trying to do,
right?
In agreement with the fabricator. And then
now,
it's all set up for you.
You did a set of rules for Oshpark, didn't you?
I did, yeah, some time ago.
Whoops, we're losing you. You're frozen. So, yeah, I was working with PCB West to do a set of design rules for them. And just there you go. You're back. You were gone.
I was just saying Oshpark have very kindly, let me switch to the other window. They were talking with me and Bill about this show and helping us sort of, they currently publicly offer a 2 and a 4 layer service, but they're moving to offer a 6, and we get to be guinea pigs for some of that. So that's what Bill was talking about earlier. They sent us a spec, and we can actually make some coupons. And in a future episode, Bill, you can break out your TDR, and we'll actually measure what comes back. And we should talk about coupons actually. I don't have a good coupon design right now. You could bring up the design you worked on for Oshpark, but I'll do a coupon as well, based on some of the coupons. IPC has actually published some coupon standards, because coupons are just a section of printed circuit board design that you send your manufacturer, and they put it on the side of the panel, or sometimes you can ask them to put it in the middle so you can measure the differences. And the test coupon, there's coupons for measuring controlled impedance and signal integrity. There's coupons for measuring for microsectioning and measuring registration. There's coupons for measuring hole drills and all sorts of different things. There's so many different parameters in the PCB fabrication process that have variability, and all of them can be measured with coupons. It's pretty amazing. And there's a whole IPC standard deck that defines what those coupons, how to construct them. And so maybe next week we can go through some of those. But show us what you did here with Oshpark. You haven't got these boards back yet, though, have you?
No. I just sent them in a couple days ago. But quite simply, when I did the Hackaday article on a cheap, and I picked a real cheap one on purpose just so I'd get good results I could show on Hackaday. But the difference between vertical and horizontal was the difference of almost 10 ohms. And that's because it was almost a single weave, right? Whereas now you've been talking about multiple prepregs. And if you put two weaves together, the chances are you don't hit this artifact of hitting the ridges in the weave. So all I did here was I put one on one layer, and I used the calculation in Altium. So the signal width on the top is like 8 mils, and the signal width in an internal layer is like 6 mils to hit 50 ohms. So I'm comparing one layer to another, and then I'm comparing one direction to another, and I do expect these to be equal just because it's a good quality board with multiple prepreg layers squished in there.
And where are your reference planes?
They're plane 2 and 5. But right. I only did it on 2. These are only on the top trio of layers.
Okay. Yeah, so in an SI coupon, I would probably include some traces that are meandering at a low angle.
I had the meander, and I closed the board without saving it. I had a meander in here.
Yeah, because we want to compare the fiber weave effect.
Yeah,
that's a way to do it. And then you want to change layers. But you also talk to us about the effect of your SMA connectors. What can we expect to see on your TDR?
Garbage. Since I threw these on here. But I use the garbage of what they call the launch. That's how I know when I'm on the board. So I never really carry, because I'm not worried about loss when I'm doing this. Okay. So you'll see the coax, and then this discontinuity, and then the PC board, and then another discontinuity, and that helps somebody like me, it's just doing it for fun, say, that part's the board itself between the two. Because there have been times when I'm going, is that the edge of the board or not? And I have to look at picoseconds versus, the length and velocity factor of the board.
Yeah. So now that people are testing materials and launches and PCBs up in a millimeter wave, this whole last DesignCon January 2020, before we all got locked down, at least a third of the talks at that conference were about de-embedding, and it's like, okay, so now it's funny to see how the industry evolves and how everyone gets onto these subjects. Like one scientist who's a leader in the field, an Eric Bogerton or someone like that, right, who's a real measurement specialist, will say, okay, we have this we're pushing the boundaries all the time. We have this new problem now that we didn't have before. So like 10 years ago, it was you'd go to DesignCon and there were eye diagrams everywhere because everything went differential. And right. and then this 3 to 2 years ago, the eye diagrams all had PAM4 because we're going to we're pushing towards DDR5 and 112 and 200 and whatever gigabits per second connectivity between boxes. So we're talking cables and connectors here. And so the only way to do that is have multiple levels of in your signaling.
Right. And I'm going to bring up an eye diagram while you're talking, so keep talking.
Bring up a PAM4 eye diagram. There's one there.
Yeah, it's yep.
So and now this year it's de-embedding for your measurement. So what that means is the art and science and the software in the instruments that costs a lot of money right now, but it will get cheaper over time, to know where the connectors and cables are, and then limit your view to only what it is you want to see. So you're essentially taking the error of the measurement itself, of the equipment itself, and subtracting all of that from what you're looking at, so that you're only looking at the characteristics of the signal on the piece of circuit board trace that you care about. And everything
you can
else
do that with a
gets
simple
subtracted
transform.
out.
Right, with just simple matrix math, you can do click and strip or whatever it's called. From the frequency domain, you can take the time domain components out of it with math that even I could do in theory.
Well, it's a subtraction, but you have to know first what's the error. So so it's like you measure your equipment first,
right?
And you capture that, and then you measure the equipment plus the thing you're measuring, and then you subtract the equipment's response that you measured first from the final response, and you get just what it is you need to see.
Right, and my point being that it's not all done in the frequency domain, that some of the information you want is the time domain, because that's your fixture before you get to the part you want to measure. So you want to remove those nonlinearities of the jig. And the only reason I know most of that is I watched Eric Bogatin has a free webinar series on TDRs and whatnot, and he talked about de-embedding at length.
Hey Bill, it just occurred to me that the comments in our video haven't kept going, even though they have kept going in actual YouTube.
Okay, because it stopped at 2:22 p.m. Hey guys, sorry about that. We didn't know that it stopped.
We're still live though, so it's all good.
Yeah,
it's just that
we're not touching it. Oh, you know what? Remember when it hiccuped? That's probably when it did it. So, what's an eye diagram tell us?
Seems there. It tells us how good our signal is through that medium, the quality of the channel.
The size of this hole here has a lot to do with how good the quality. As these fudge together, this hole can close, and once it closes completely, in theory, you can't. It becomes very hard to extract the information that's contained in there.
Yeah, it's all about statistics at this point.
It is statistics, yeah.
Bit error rates. It's like the software in our systems, and some of that's custom ASICs running error checking and things like, and that's another topic.
There's PyBert also.
This is another topic we should talk about, because it relates to DDR5, and they seem to be pushing back actually building any DDR5 chips, but this subject of forward error correction is just super elegant.
FEC,
yeah, but we'll talk about that in another
emphasis,
episode.
Pre-emphasis, that kind of thing.
Yeah.
So they not only simulate, a PC board or whatnot, or the circuitry, the connectors, but when they simulate, they have a BERT tester, bit error rate tester, written in Python, PyBERT. So they can create stimulus at a software level and tell you the predicted error if you were running a true physical BERT test, in theory.
Yeah. So we know we can tolerate, 1 bit wrong out of every how many billions.
Right.
And we are dealing
exactly.
Gigabits. We're dealing with billions of bits per second here now, and it may depend on the data. If it's streaming audio and video, you can tolerate a lot of errors before the end user will notice. But if it's a file download to install a program, you can't tolerate anything. So you've got to have error correction built into those. So all of that's a well understood and solved problem in software.
Hamming codes and stuff, yeah.
It boils down to is the benefit of the extra power expended and the increased number of errors, sheer number versus the percentage, is that offset by the other benefits we get from going so much faster?
Right.
So anyway, so we have to go to PAM4. Now this is interesting. I asked a semiconductor product manager from one of the companies that makes the IP cores for doing PAM4, reading and writing at high speed. I asked him, so how do you get the 4 levels? And that's a banal question. He probably thought I'm some knuckle-dragging PCB designer, which I am. I'm at a, but he politely said, I said, in the IP, how do we get the 4 levels? Because I'm thinking of loss.
Right.
Thinking of loss.
Right.
If you're going to one voltage and then another and another, like there's discrete voltage levels, how do we do it? He's like, oh, it's a DAC. It's a DAC with 4 levels, a 2-bit DAC. So we have a 2-bit DAC, and yet we look at this and this would be classed as digital signaling because it's ones and zeros, but it's not ones and zeros. It's 0, 0, 0, 1, 1, 0, and 1, 1 because there's 4 levels. So now finally, going high speed is pushing. This always tends this way. Getting high speed digital tends to push us into the more analog sort of way of doing things, and that's never going to change.
Right.
So we can go 40, 80, 112, whatever gigabits per second. We have to use analog techniques to do it. And that was the same when we wanted to go 300 bits per second over POTS telephone wires.
Yeah, I did some of that work with T1 signaling 1.54 and E1 signaling 2.048 megahertz. I mean, and we were like, oh my God, I can get a megahertz down a pair of twisted wires, and it was just pre-emphasizing the heck out of the signal, so that you would pre-emphasize the highs and you might delay the lows, phase group delay, so that when they all arrive, they arrive at the same time, and the signal looks right again, even though when it left the transmitter, it might not look right. So you can actually...
So what does the pre-emphasis do? I look at pre-emphasis and I see it as a kind of high-pass filter that boosts some of the higher frequency content of the signal.
Right. And then there's some delay factor too, because signals don't travel the same speed down a coax based on their frequency. They're literally bouncing back and forth, if you think of fiber optics, more than a low frequency signal would. So you get these delays, and you have to, part of the pre-emphasis is getting those delays lined up.
That happens in the PCB as well because of the non-uniform dielectrics, and the dielectric constant of the glass fiber and epoxy composite varies based on frequency. So,
yes, it does.
So your signal
everything varies based on frequency.
Yeah. So your signal at higher frequencies will travel more slowly in the board than at lower frequencies.
Right.
But that doesn't make sense to me, but it's along those lines. So you get this smearing or distortion in the channel, and using eye diagrams, we can measure all of those things. That's why we like equipment that presents signal integrity measurements in the form of an eye diagram. You can measure all of those characteristics by overshoot, undershoot, the width of the crossovers, and the openings in the eye.
And even a square wave, you mentioned overshoot and undershoot. back in the days before I had eye diagrams, I would look at a square wave and I could tell you a lot about the integrity of that signal by how well the square wave is reconstructed or represented. So, and with TTL and even CMOS, if you picture a square wave in the ringing, there's something that says the logic high isn't true until the ringing stops, depending on the ringing or the low. If you're below ground and then above ground and below ground, that ringing subtracts from your usable propagation time. So, hey, we're coming up on the hour here in 4 seconds. So it's been an hour and 15 since we did this. I got the chats to work again. Somebody was asking about making capacitors with the different the different copper. And I'd say, yeah, if you get your power and ground reference planes close enough together, you get a slight bulk capacitance effect. But now, have you made capacitors out of copper?
Yeah, and there's tools. There's tools to calculate it. That I've found even online. If you go to Microwaves 101, they have one of these. There's a capacitor calculator. Then I think Cooks has one built in. There's a capacitor calculator.
Well, I want you to show us Cooks sometime. The simulation tool is what we're talking about. Let's bring this up real quick.
Let's bring this up real quick.
All right, hang on. I'll get mine out of the way.
Let's see. Let me find it.
And here's your screen share. Whoop, there we go.
Give me 1 second here. I've got to launch it direct from where I installed it. Actually, this is Cook's Studio, which is a derivative of Cook's.
Right. And we could do a whole show on it, and maybe we should at some point. Next week? Oh, hey, will we be here next week? I rather doubt it, and the week after, right? Because it's Christmas Eve and New Year's Eve.
I'd be willing to do a New Year's Eve, Christmas Eve. I won't be able to. Why are you getting the Skype thing from me? That doesn't make sense.
Because it was working earlier.
Oh, it's because the application hasn't fully launched yet or something? Where is it? It is launched though, but where is it hiding? Oh, here we are. So I'm going to go full screen and switch window. Can you see this? This is Cook's
starting
Studio.
to work.
Unfortunately, being open source, they have not done a tremendous job of supporting higher resolution monitors yet. But there's this tool in here, Component Designer. Why is that not showing? That's ridiculous.
Oh, see, that happened to me when I tried to. That happened to me when I tried to show the IP Lab IDE.
I'm just going to go share the whole monitor instead of if I share the whole monitor instead of the application, it ought to.
There it goes. Yeah,
there it is.
Here,
so this is
I'll
cool.
zoom in.
I really like this little tool.
That is cool.
I can design inductors, planar inductors, and parallel plate capacitor.
Cool.
And so, so this is using formulas from Brian C. Waddell's book, I believe, which are well trusted. They're really accurate across a very broad frequency range. And this, you can include the fringing field. You can see that makes quite a big difference. But if I put, see, the default permittivity all through Cooks is alumina because they assume you're designing RF components like chip capacitors, integrated circuits, amplifiers, and the alumina epsilon R is 9.8. But printed circuit board, they've got some Rogers material in there.
Like 3000 series FR4. Or something?
Yeah. Rogers 4000's in there, and FR4. And you can see with FR4 with a half, it's even less than half the epsilon R of alumina, so you get half the capacity or less than half the capacitance.
Right.
Because that's what permittivity is. It's a measure or a parameter of how much energy can be stored in an electric field in that material. And in a given sort of space.
And understanding energy in the field, is to understand inductance too.
Right. So if I have two planes in a printed circuit board, and they are not 1 millimeter height, but let's go for mils, and say we have a 4 mil thick prepreg with power and ground between them. I don't know if there's any way. Maybe I should share. Let me switch to share.
Well, I'd actually suggest, why don't we save this, keep our powder dry, and do a whole episode, or at least start an episode on cooks and see where it leads. Hey,
right.
That's working though.
Yeah, that's a bit better. So I'll just do this part, and then we'll close out the screen for the day. But we can do.
More. Now it's readable. Right. Yeah, very good.
Yeah. So if you have two planes and you have a 100 millimeter by 80 millimeter board, let's say. So that's and 4 mils. Then we get 3 nanofarads, which is not bad.
No, that's not.
That's assuming you have unbroken copper planes. But of course, we know they're going to be like Swiss cheese with all the holes and vias going through them. So it's not going to be anywhere near that. It'll probably be less than half that. But you can still see, if you design your layer stack up right, you can get a reasonable amount of capacitance. It's very, very low impedance capacitance because of the physical structure of this. There's more that comes into it and so on. But if I did a 2-layer PCB, so it's going to be 1.5
where there's
millimeters.
A huge distance between the layers.
The height is 1.5 mils. No, 1.5 millimeters. We only get the order of 200 picofarads, and that's plus a little bit more for the fringing field. And you can see the fringing field is just a little additional capacitance around the edges of this thing. And it doesn't make a big difference for a large printed circuit board area. But if I have a very small structure, like I'm making a 2 millimeter by 1 millimeter capacitor with, let's say I'm making an actual chip capacitor, say, and I have 2 mils thickness in the dielectric, I get 1.8 picofarads. If I remove the fringing field, it's I don't know.
It's a percentage, yeah.
But they're removing quite a bit.
It looks like 30%.
Yeah. So fringing does make a big difference.
15.
And that's fringing fields are taken into consideration by accurate impedance calculators.
Right.
Let's
stop there.
Yep.
My Christmas tree just arrived upstairs. I can hear it, so I'm going to have to go up and drag it in the house, chainsaw the trunk.
I'm glad you just got yours, because I thought I was really late getting mine when I got it. Mine arrived on Tuesday or Monday night. And I thought I was late.
I kept threatening to go onto the back lot here and cut a tree down, and none of them, they're New Jersey trees, none of them look like you would buy from the Great White North, right? But I liked them. My wife, no, we are not using one of the trees from the backyard. And my backyard's 10 acres, so, I had something to choose from.
You want one in your front yard that's an actual beautiful tree, and each year you just decorate it, put lights in it. That's what I would love, but,
I planted 2 of those, and they're now so high that the electric company has to take the top off of them because they're getting into the power line.
I hate that. That's tragic. There's nothing... Well, there are worse things. There aren't many worse things than seeing a tree that's just brutalized by the power company.
Yeah.
Hey,
anyway. Let's talk about HDI, too, next time. Let's talk about high density, the rules that go along with it.
Sure, and we could maybe scout out some of the PCB fabs and see if we can compare notes on cost as well. Because I've never actually sent an HDI design to fab.
Neither have I. No.
I've had lots of customers do it, they don't share details about what it cost them.
And they may not share all the information about what they found empirically, because that's the juju that they learned the hard way.
Yeah, that's right.
So, yeah, somebody just said, have a happy holidays. Hello, Mr. Hurd, somebody lug nuts. Yeah, happy holidays to everybody else. Somebody actually said that next Friday is actually Christmas, not Christmas Eve.
I think that's true.
I think that's true too. Don't get old. Don't get burnt out. You can't even tell what day Christmas is or how to add 7. But that's me. That's the life I chose. So. Well, it's good seeing you again, my friend. And so I'm not going to be doing this on Christmas. That's a fair bet. And maybe New Year's we can do something, but I doubt that people would be on their computer. I don't know. Maybe they'd be a lot on their computer. So.
Well, or we could do it the day before or 2 days before.
Well, I was going to say, if we kept having
we could record something and put it up and sort of...
If we kept having the problem with live streaming that we were having, that was going to be a conversation you and me had about pre-recording. So, pre-record it and then we join the chat, right? To just chat along with it.
How about we do this? Next week, maybe Wednesday, we just record something and have it go live Christmas.
Only if you wear one of those Santa's hats for the show.
I could do that. I could look like an elf. Yeah. We're getting smileys in the response, and Dave's saying, "Give us something to do." Dave, I don't know what your situation is, but I feel for you that you would turn to watching us live stream on Christmas Day or on a holiday.
Our condolences that you find this interesting.
You want us to go live on Wednesday? That's an option. Well, I tell you what, we'll talk about it offline. And no, we haven't. I'm sorry, we have not looked into making a Discord, but I need to do that. And
I'm so old, I don't know what a Discord is, so I leave it to you younger folks. I know what it is, but I wouldn't know how to set one up.
I've been so swamped with work, I apologize. But now Autodesk has this wonderful thing. It's like an annual week off because they realized most people in the company just took this week off anyway. And it's a great company to work for. And one of the things they did this year because of COVID and the stress, everyone's been really pushing hard and doing well. So they said this year take 2. So one of the things I will be doing during my time off is getting on top of my projects and excuse me, and sorting some of these things out for Bill and I to talk about coming up in the coming year. So, so one of those things will be getting the Discord going so we can all chat with
Discord,
each other.
Right.
Yep.
So, excellent. Well, again, good seeing you. Yeah, thank you, everyone. And we're going to stop there. It's been almost an hour and a half, and I'm sure we could keep talking, but we're going to stop now. So thank you, everybody, and everybody have a safe and happy holiday.